Hello everyone, we will finish the last session of today's lecture. So, we talked about how we convert from the geocentric coordinate into the 6 orbital elements. Now, in the reverse way, the second problem we are going to discuss is from the 6 orbits elements. Into the r vector and the v vector in the geocentric coordinate system. To get this conversion is not that easy. So first, let's think about with the orbital elements h, e, capital omega, small omega, I, and theta. What information we have? Actually, with just the h and e in the orbital plane, we can find out in the h and e. For example, if here is the focus, and we can set up in the orbital plane the two-dimensional space, the small x bar and the small y bar, and also we have the key unit, which is the small z. So in the orbital plane, we can find out just from h and e, we can find out a vector r in the orbital plane, or we call it the perifocal frames. The vector r in the perifocal frames, it is expressed by, so this r here, to make it different from the r in the geocentric frame, we assume this is rx bar, and it's expressed as h square mu 1 divided by 1 plus e cosine theta. This is the magnitude of r in the perifocal frame, and then later we have cosine theta. Then this cosine theta is unknown. This x, small x, we use to make it different. I use the small x bar hat plus sine theta, small y bar hat. And this z component, since the motion is only restricted in the two-dimensional orbital plane, the z component here is 0. I use z bar hat 0. And how about velocity component? Velocity, again, to make it different, I use the velocity x bar to represent the velocity in this orbital plane. And it's equivalent to mu divided by h negative sine theta x bar hat plus e plus cosine theta y bar hat plus 0z. So again, the v velocity evaluated in the orbital plane is also has two components. Its z component is 0, so their motion can be restricted in the orbital plane. Okay, with the h and e component, the two orbital elements, we can express the vector of the satellite in this perifocal frame, or we call it orbital frame. However, our objective is vector r and vector v in the geocentric frame. So we didn't get the final solution yet. The temporary vector r and v, they are not in the geocentric frame. They are actually just in the perifocal frame we set up. So we need to convert a vector from one reference frame to another reference frame. That is, from the perifocal frame to the geocentric frame. So next step, if we can convert this vector from one reference frame to another reference frame, we will get the final solution. Then the question is how to convert the two different coordinate systems. Then it related to the rotational matrices. If some of the students here took my flight dynamics class before, that's 13520 or 13521. So that class, we talked about the rotational matrices. We also says about any vector in the three-dimensional space can be rotated to another vector following three rotational sequences. And to understand it better, I also prepared some movies, and this movie talks about the three rotations along x, y, z. So this is the first rotation along the z-axis, and the second rotation along the x-axis. The last rotation is along the y-axis. So those are the rotation in the three-dimensional space relative to the three different axes. And for each rotation, their vector in the two different frames can be expressed by a rotational cosine matrix. So this is the rotation about the x-axis. And the next is the rotation about the y. And later rotation about the z. And for the three continuous rotations, we can multiply all three rotational matrices to get their final position. So this is one example you can show here. Now, to solve our problem, we have to do it step by step. In case some of you here not familiar with the rotational matrix, we will explain it here. So I prepared a set of rotations. The first is a rotation about the key axis. So what does this rotation tell us? So if I have this rotation, we are going to have the vector. If we rotate with respect to the key head axis, choose the I prime, J prime, and K prime space, then the vector I prime, J prime, and K prime can be written as the rotational matrix. Cosine phi, sine phi, 0, negative sine phi, cosine phi. It times the original axis I, J, and K. And this rotational matrix, we call it the R1 rotational matrix about the phi angle. And if you can see, if this is not a unit vector, it's some vector evaluated in the I prime, J prime, K prime, we can replace it. If it's the R vector prime, we can use the same thing. If it's originally is R. So that's how we make this conversion. So the next, we'll talk about the rotation about the J-axis. The rotation about the J-axis, we can use something similar. And at this time, if we rotate to the I prime, J prime, and K prime, the rotational matrix can be written as cosine phi, 0, negative sine phi, 0, 1, 0, sine phi, 0, cosine phi, and times the I, J, K. And we name this matrix as the R2 matrix. Now the next one is rotation about the I-axis. And similarly, we will write I, J, K prime equivalent to the cosine phi sine phi 0 negative sine phi cosine phi 0 0 0 1 I j k. And this matrix we define it the R3 matrix. So this tells us the rotational matrix according to different axes. So if we make 3 sequential rotations with respect to the k, j, I, we can multiply them together. For example, if we make a rotation from the k followed by the I followed by a j and followed by a I. So k is k1, j2, I3. The k1 we make a rotation about phi 1, j2 we make a rotation about phi 2, and for I3 we make a rotation about the phi 3. So eventually if we have a vector v3 and it can be expressed as the R1 phi 1 initially it's v0 vector times the R2 phi 2 times the R3 phi 3. So that's how we convert a vector through the rotational matrix. Now we come back to our problem. What is the rotational sequence we have in our problem? And to explain this, I will insert another picture. So this explains the rotational sequence. And to make it clear, I will also insert another set of pictures that explains how we can convert from the PQ. PQ is the x bar, small y bar axis we defined to the capital X, Y, Z axis. So this rotation is actually rotation first around the key hat through the right ascension angle omega, and it rotates the I and j, as you can see, into the I prime and j prime with respect to the k axis using angle omega. The first rotation, okay, let's first write down rotation with respect to the key axis of angle omega. So since it's the key axis, we can write R3 omega. That's equivalent to cosine omega, sine omega, 0, negative sine omega, cosine omega, 0, 0, 0, 1. And next, the second rotation is around the node 9, I prime, through the angle I. And we call it, since it's rotation about I, we use R1. I, that's equivalent to 1, 0, 0, 0 cosine I, sine I, 0 negative sine I, cosine I. The last rotation is also the third location, is in the orbital plane and rotates the unit vector I prime and j double prime through the angle omega, as you can see from this. That's the last rotation. It's a rotation with respect to the z-axis, so we have R3 again of omega. We get cosine omega, sine omega, 0, negative sine omega, cosine omega, 0, 0, 0, 1. So we have those 3 rotations, and then we multiply all of them together, as we said. The rotational matrix, we can use the first is R3 capital omega. The second, we have R1 of angle I. The third, we have R3 of angle small omega. And we multiply them together, and eventually the R, we have is equivalent to the Q times the R in the capital X. Q times the R in the capital X. Or we can say the R in the capital X equivalent to the Q inverse of R in the small x. And the same thing, we can write out the V in the small x is equivalent to Q V in the capital X. Or the V in the capital X equivalent to the Q inverse, the V in the small x. So this finishes the last point we want to discuss, that is from the 6 orbital elements into the r and v vector in the geocentric coordinate. So remember, what we did is we first find the vector in the orbital plane, then using the coordinate matrix transformation, using the coordinate transformation through the matrix, rotational matrix, to convert them from the orbital plane to the geocentric plane. That's all we will discuss today, so I will see you next time.